Question 24, 7 marks. The boiling points for two series of compounds are listed. Plot the boiling points for each series of compounds against the number of carbon atoms per molecule. So what we're going to do here is simply plot the boiling point on the y-axis. As we can see from the data, the lowest boiling point is -6 and the highest boiling point is 118 Celsius. Now we simply fill in the data. The first amine is -6. The next one is 17. Propylamine is 48. Then butylamine is 78. Now that's the alcohol. Methanol is 65. Next one's ethanol is 78. Propanol is 97. And butanol is 118. In this part, we are going to look at how to fashion a response that will give us maximum marks. So let's look at question 24b. With reference to hydrogen bonding and dispersion forces, explain the trends in the boiling point data of these compounds within each series and between the series. Let's look at the sample answer given by HSC. For both the alcohols and the amines, dispersion forces will increase with increasing carbon number due to increased number of electrons present, leading to increased boiling points. However, for any given carbon number, the alcohol has stronger hydrogen bonding than the corresponding amine, as oxygen has a higher electronegativity than nitrogen. So the alcohols all have higher boiling points than the corresponding amines. Personally, I feel that the sample answer given by HSC is minimal and basic. In the following slides, I'm going to develop the complexity of the response. Let's think about all the relevant content we can use to fashion our understanding. If we go back to the question itself, the main points are within each series and between series. This is a typical comparison that you will find in HSC questions. In this slide, I would just like to list all the different aspects and then later on put it together to give a full picture of the system. Point number 1, we are looking at homologous structures for both the amines and the alcohols. So as it goes, we are presented with carbon 1 to carbon 4, and in this case amine versus alcohol. Point number 2, all the amines in this question are primary amines. Similarly, all the alcohols in this question are primary alcohols. So then we can now definitively compare the two because both are of the primary sense. Point number 3, we can see from the graph that overall alcohols have higher boiling points than amines. This is relevant to between the series. Now we have to consider why that is the case. Point number 4, oxygen versus amine. Oxygen is more electronegative than nitrogen. If we look at the lone pairs between alcohols and amines, this is what we see. In alcohol, there are 2 lone pairs. In amine, there is 1 lone pair. We are looking specifically the interaction of the adjacent water molecule. So since we know that oxygen is electronegative, so we're going to have a dipole moment of delta minus, which makes the hydrogen to possess delta plus. Since oxygen has 2 lone pairs, that means it can effectively have 2 hydrogen bonding sites. Now if we draw another water molecule, we can show 2 hydrogen bonding sites, that being 1 and that being the second one. If we compare that to amines, we get a different story. Amines have 1 lone pair, and so it can only effectively have 1 hydrogen bonding link through space. Point number 5. Within the homologous structures of either the amine or the alcohol, as you increase the carbon chain by 1 unit, the resulting boiling point will increase. Point number 6. So if we're looking at hydrogen bonding within the series, then there shouldn't be much difference between the first carbon to the fourth carbon, because only the carbon chain increases. So let me demonstrate. So this is methanol, this is ethanol, propanol, and lastly butanol. So as you can see, the only thing that changes is the additional carbon each time we go down the list, yet the hydroxy remains the same. So hydrogen bonding within the series is not going to affect much change other than the fact that it can do hydrogen bonding. What's more interesting is to look at the relationship of the increase in one carbon chain unit. So that's where we're going to lead the conversation to dispersion forces in point number 7. So effectively in this question is the relationship between dispersion forces and hydrogen bonding. What we can say about it is dispersion forces are going to be temporary and hydrogen bonding forces are going to be permanent. Henceforth, why this is weak and this is strong. Now let's go back to looking at the increase in carbon chain. How does that affect the boiling point? So point number 8, each time you increase the carbon chain, you're only increasing it by 1 unit of CH2. So let's visualize that. CH3OH is methanol. CH3, now we add 1 more unit. That is ethanol. Let's continue. CH3, CH2, we now add 1 more unit. That is propanol. And then we add 1 more unit of CH2. And that makes butanol. So what you are essentially doing every time you're adding one set of CH2s to lengthen the chain of the carbon backbone, you are introducing 6 electrons. As you add more electrons to the carbon chain, it increases the dispersion force. So this explains why within the series that both amine and alcohol sees an increase in boiling point as you go from C1 to C4. In summary, we can say that as one carbon chain increases, it increases the size of the molecule. When the size of the molecule is small, then the predominant force will be hydrogen bonding. However, when the size of the molecule is getting bigger, then the dispersion forces becomes more predominant. That is the difference between the two forces in terms of size. When writing the response, I recommend you to construct the response in terms of within the series and between the series. This is because that it outlines very clearly what the question wants you to achieve. Within the series, as the carbon chain increases from C1 to C4, the dispersion forces accumulate due to additional electrons. Consequently, the boiling point also increases with chain length as illustrated in the graph. The relationship between dispersion forces versus hydrogen bonding is as follows. The intermolecular forces of a short chain alcohol or amine is predominantly hydrogen bonding. Similarly, the intermolecular forces of a long chain alcohol or amine is predominantly dispersion forces. As chain length increases, dispersion forces become stronger, while the corresponding hydrogen bonding forces are minimal. For the same chain length, the boiling point of alcohols is greater than amines, because an O atom is more electronegative than a N atom. Moreover, based on the number of lone pairs, an alcohol group can have 2 hydrogen bonding interactions with its adjacent neighbors compared to only 1 for amines. Therefore, more thermal energy is required to break the intermolecular forces in alcohols compared to amines of the same carbon chain length. So on this slide, it shows the final response. Thank you for watching, and I'll see you next time. Please follow and subscribe to this channel For more quality contents,